Okay, so today we're going to talk about algorithmic complexity. So first we'll take a look at how functions grow. You'll see that I've put down 4 functions here. F of x is equal to x plus 1, f of x is equal to 2x, and so on. And you'll notice that the value of f of x increases at different rates for each of these functions. So for example, if we took f of x is equal to 2x, f of x increases by a factor of 2 for every x, but if we plotted f of x is equal to x squared, f of x increases quadratically. So now we'll take a look at the definition of big O notation. So we'll take 2 functions, f and g, and we'll say that f of x is big O of g of x if the absolute value of f of x is less than or equal to the absolute value of g of x multiplied by some constant c for all x is greater than k. This is a little confusing right now, so we'll go over an example and that'll hopefully clear it up. So we're going to show that x squared plus 2x plus 1 is big O of x squared. And to do that, we'll find a constant c and k such that the absolute value of x squared plus 2x plus 1 is less than or equal to the absolute value of x squared multiplied by c for x is greater than k. And this usually involves a bit of guesswork, so let's just assume that k is equal to 1. And therefore, the minimum value of x is also equal to 1. And if we plug in x to our equation here, we'll get 1 plus 2, the absolute value of 1 plus 2 plus 1 is less than the absolute value of 1 times c. And then simplifying, we'll get 4 is less than or equal to c, so c is equal to 4. Another way to look at this is with a graph. So I've plotted 3 functions here. X squared is the red line, x squared plus 2x plus 1 is the blue line, and 4x squared is the green line. And you'll notice that beyond this point, which corresponds to x is equal to 1, you'll notice that the green line has a greater value than the blue line on the y-axis. And this, you'll also notice that the coefficient of the green line's function is 4, which corresponds to our value for c, and our value for 1 at this point corresponds to our value for k. So now we'll look at how time complexity comes into play with actual algorithms. So we'll first consider the operation x plus 6, and we'll assume that all basic operations such as this one take a constant amount of time. So since each operation takes a constant amount of time, we have to find a function that given input gives us the total number of operations if we want to find the time complexity of a program. So for this program, we'll notice that it's just a for loop that goes from 0 to n, and for each iteration, we'll execute 1 operation. So the total number of operations executed in this program is a function of the input, and it comes out to f of n is equal to just n. If, for example, we had a nested for loop, we'll change our function to represent that. So for each iteration in the outer for loop, we'll have n more iterations, and so our total number of operations becomes n squared. So now that we have our function, or our total number of operations, f of n is equal to n, to find the big O notation for this function, we'll find since each operation takes a constant amount of time, we'll call it c. Our function becomes f of n is equal to nc, and now all we have to do is find some function g of x such that the absolute value of nc is less than or equal to the absolute value of g of n multiplied by some constant big C for all n is greater than some constant k. And it follows that if we make c equal to little c and k equal to whatever, and g of n just equal to n, we'll get the absolute value of nc is less than or equal to c times the absolute value of n, and these are equal, so therefore nc, or this program, is big O of n.